Really? Good morning, everyone. First, I would like to thank the organizers for inviting me. Especially, I would like to thank Professor Shaif. Uh, I still remember my visit to Pakistan about 3 years ago. So it's good to see some familiar faces just now online. Today, I'm going to talk about light rings and quasi-black holes. They are also related to black hole shadows and quasi-normal modes. This talk is based on two of our recent papers, like this. Here are our motivations. What is a light ring? Actually, a light ring is a circular photon orbit outside a black hole or an ultra-compact object. Light ring is very important because it's we cannot see a light ring in Minkowski spacetime. It has some feature of the curved spacetime. A light ring also plays an important role in gravitational wave observations and black hole photographs, like the image of M87. According to Vita Cardoso and some other authors, light rings could be observational evidence for event horizons. Actually, it could be a signature of black holes. We'll focus on that later. Here is a simple example of light ring in Schwarzschild black hole. We are familiar with the Schwarzschild solution, and we can study the orbit on the equatorial plane, CT equal to pi over 2, and the full momentum of the photon. So recently, we studied this issue, and we don't use the topological argument, which we think is complicated. Actually, we use a much straightforward approach, and our result is even stronger. In our arguments, only some generic conditions have been used, like the asymptotically flexed conditions. But our results are even stronger. So I don't have time to show the derivation. So I only introduce our results. First, for non-extremal stationary black hole, we can show that there are at least two light rings. So this conclusion is the same as Kukas, but we have some more specific results. We can show that the outermost light rings are always unstable along the radial direction and stable along the angular direction, and the inner light ring is always stable. And our argument can also prove that for extremal black holes, we can show that there is at least one light ring. So this is a new result. And when the space-time possesses a reflection symmetry, we can show that there must exist at least one light rings on the equatorial plane. And we can show for horizonless spacetimes, our argument can also apply to horizonless spacetimes. We can prove that if light ring exists, there must have at least two light rings, and the outer one is unstable in the radial direction, and the inner one is unstable, the other one is stable. So why is that? So we have the two pictures. According to our analysis, the potential at the center is always divergent, and at infinity, the potential goes to zero. So the potential can decrease monotonically like that. So there's no minimum or maximum, and that means there's no light ring. But we have also the other possibility. The potential can just go down and go up and then go to infinity. So that means we can have a minimum and a maximum. So this is the stable light ring, and the other one is the unstable light ring. So our argument is much simpler. So this is our conclusion, but we have further questions. We just showed for horizonless spacetimes, we cannot guarantee the existence of light wings. So we want to know under what conditions we can have a light wing for the ultra-compact stars. And we also want to know if the appearance of light wing is related to the stability of spacetimes. Actually, this issue has been explored by Rita Cardoso and other authors in 2014. They conjectured that ultra-compact objects, if they possess light wings, they may not be stable. How could they get that conclusion? They just calculated the quasi-normal modes of ultra-compact stars, and they found that long-lived modes near the stable light wing. And we know long-lived modes means the spacetime is unstable against the nonlinear perturbations. And if this conjecture is true, that means if we say light wing, it must be black hole. So light wings could be a signature of black holes. And the model discussed by Cardoso has some limits because in their model, the star always has a radius smaller than 3m, and outside the star is just the Schwarzschild solution. So in their model, the existence of light wing is guaranteed. But we want to explore this issue further. We want to have some new models. In that model, we wish that we have a series of solutions, of horizonless solutions, and we can change the parameter, and we wish to see at what conditions light wings can appear at certain parameter. So for this purpose, we visited the quasi-black hole solutions. These solutions were constructed and discussed firstly by Lemos and Weinberger about 20 years ago. This is one parameter family solutions. The interesting thing is that such solutions are non-singular everywhere, but they can come arbitrarily close to a black hole at certain critical parameters. So let's see the solution. We start from the Einstein-Maxwell equation for charged dust, which takes this form. This charged dust here, rho is the energy density, and we also have they should satisfy the Maxwell's equation. And we are interested in the extremal dust solution. That means the energy density is equal to the charge density. This solution is interesting because in this way we can balance the gravity with the electrostatic force. So it has a lot of applications. And such a solution can have this form. Here we use the capital R. It is not the Schwarzschild radius. But in this solution, there is only one function, unknown function, capital U, and using Einstein's equation, we can get this solution. We can have the energy density related to the metric. Specifically, we can choose U, capital U of R in this form. Here, Q is the total charge of the spacetime, and C is a parameter. So the parameter C can change continuously. When C goes to 0, the solution just reduces to the extremal less than not strong black hole. And R, capital R equals 0 is just the black hole horizon. So this is a series of solutions, and it can reduce it to the black hole solution. And the area radius of the small r is related to the capital R in this way. So it's interesting to say if we take the limit c equal to 0 first, that means we start from a Rn black hole. Then we let capital R equal to 0, we can have R equal to Q. That means this is just the horizon. But if we change the order of the limits, see we let capital R equal to 0 first, but we keep C not equal to 0. So C can be very small. But from this equation, we see as long as C is not equal to 0, capital R equal to 0 just means the small r is equal to 0. That is the center of the quasi-black holes. So that tells us the results. The results just depend on the order of the limit we take. So as long as C is not equal to 0, we always have a quasi-black hole spacetime. It has no horizon, and it describes a compact star. So we have the R equal to 0 at its center. So next, we shall calculate the light wings for the quasi-black holes. So the procedure is the same. So we can have the radial equation. We have the potential. Here V is the function of capital R. So we are looking for the light wing. We introduce some variables, but I'll skip the details. We still need to calculate the derivative of V to find out light wing. And so here is the important part, because basically this equation is a cubic equation. So we can calculate the discriminant delta here. So when delta equal to 0, we have a critical constant k, which is equal to 2 over 27. So when c squared is bigger than k, we have a real root, but this root doesn't give a light wing because r is smaller than 0. So for delta equal to 0, we have a degenerate case. It gives 2 degenerate light wings. For delta smaller than 0, i.e. c squared is smaller than k, we can have 3 real roots, but we only have 2 roots corresponding to light wings, R0 and R1. This is the picture. The blue line just the critical curve. When c squared is equal to 2 over 27, we have degenerated light wings. But for the purple line, if the c squared is bigger than 2 over 27, we have no light wings. There's no extreme. But the red line is interesting because for c squared is smaller than the critical value, we have a minimum and a maximum. So we have a stable light wing here and unstable light wing here. So this so the critical value just tells us when the light wing can appear, and we should pay attention to the black hole limit. When c goes to 0, we can expand the roots in this way. Actually, the result is we see when c goes to 0, we can have 2 light wings. As long as c is not equal to 0, we always have 2 light wings. But when c is just 0, that's the extreme black hole, iron black hole. We also have 1 light wing. So the outer light wing is the same size, has the same size as the black hole, but we have a new light wing inside this one. So that's I think that's an interesting result, because when c goes to 0, the matrix just reduces to the extreme black hole. But the light wing, we just have the number of light wings just jumps from 2 to 1. This is due to the we just mentioned that the result depends on the order of the limits we take. So next, we will talk about the long-lived quasi-normal modes. So we want to study the stability of the space-time. So the master equation is just this. So when S is equal to 2, we have gravitational perturbations. So we want to we assume the time dependence is in this form. So omega is the frequency. We want to find the quasi-normal mode. And the radial function just satisfies Schrödinger-like equation in this form. Okay. And here we can write the frequency in the real part and the imaginary part. Since we have assumed the time dependence in this form, we see the amplitude of the perturbation will grow exponentially if the imaginary part is bigger than 0. But even if omega I is negative, but if its amplitude is much smaller than 1, we still can have a long-lived mode. That means the perturbation can survive for a very long time. And that's so-called long-lived mode. But if we have a long-lived mode, usually the space-time is not stable against the nonlinear perturbations. And we should also notice that in the atonal regime, which means L is much bigger than 1, the potential V to L is always approaches the potential. This we just mentioned. This is the potential for the no geodesic. So we have the same picture here, but the V is no longer the potential for geodesic, but it's the potential for the quasi-normal modes. It also has they have the same critical values. So we can calculate the quasi-normal. We calculate we choose c squared is equal to 1/27. So that means that's the red line. That means we have two light beams, and we have one stable light beam. So we can use both WKB method and the numerical method. So the red dot here is obtained by the WKB method, and the blue dot here is the numerical solution. So we should pay attention to the lower half because that's the imaginary part of the frequency. So the result shows that the omega I, the amplitude of omega I is much smaller than 1. That means we have long-lived modes. So when light wings, when we have light wings, we have long-lived mode, and the space-time may not be stable. And if c squared is bigger than k, that means it's bigger than that. So there are no stable light wings. So we can follow the similar analysis for planar ABS black holes given by. So these results are given by the two authors about 10 years ago. So we can show that there are no long-lived modes. So it seems from this model we can see the connection between the light wings and the stability of the spacetimes. So we can give some conclusions. First, we found just a critical parameter for the quasi-black hole, where the light wings just appear. In the black hole limit, we found one stable light wing, which just coincides with the iron black hole. But we have another new light wing, which is stable. But such a light wing doesn't have the black hole correspondence. We then calculated the quasi-normal modes of the quasi-black holes. Both the WKB result and the numerical result shows that long-lived modes can survive for the range where just the stable light wings appear. So this indicates that the horizonless spacetimes with light wings are unstable. So our work just provides an explicit example that light wings could be direct observational evidence for black holes. That means when we see a light wing, we can almost be sure that the object is a black hole, not a star, not a horizonless star. So I think this is a support to the conjecture by Vitor Cardoso. Okay, thank you very much for your attention.